out to the computer. Okay, so yeah, I updated the schedule with regards to the midterm tests. And then as soon as I posted the schedule, I realized I didn't put the quiz schedule on there. So I need to do some more again. Maybe I'll make it to like tentatively, it'll be like every other week. There's what, 2 or 3 more quizzes left? Let me really check here on the show one. We had, where is it? Course information. Yeah. Values of each one, quiz 2 and quiz 3. Okay. So we have one more quiz, midterm, and then one more quiz, and then the final. Make sure everybody else is trying to get back in. Okay, cool. All right. Okay. So yes, today we're talking about HPLC for the first time, and like should be a pretty, I guess there aren't too many slides in this section. There's 32 slides, but I find the theoretical concept of like the plate and stuff, I find really hard to get my head around, at least the first time, and it still like gets me in certain things. So we're gonna take it slow, work on it together, and we'll focus more on like the actual practical aspects of knowing plate count, right? Not so much the deep theory stuff, right? We're gonna worry so much about how it would affect your life if you were working in an actual lab. When would this actually matter to you? Those are the things I like to focus on mostly in class, right? Because those are the things that will come up in your day-to-day workplace, right? You know what? I do like it on screen like this. Okay. Good stuff. All right, so we have these lecture slides, then we have those usual weekly questions, which I posted as well for you guys. And so if you can answer all of those questions, then you guys will be very well suited to doing quizzes and tests that are coming up. And I'll make sure that you guys know as soon as possible what content will be on the midterm. I know because the midterm that the previous professor had set up, it's based on week 5. So it would have been only like week 4 and 4, which I'm okay with. I just want to make sure we cover everything that's on that as well. So let's keep going. So just as a brief refresher, right? Your classic chromatography setup has gravity-based filtration, right, through your stationary phase with your mobile phase pulling your sample through or your analytes through, right? So individual components separate as they travel down the column. So in this case, this looks similar to your guys' spinach experiment you guys worked on last week. Did that work out? No? It always throws you for a loop, doesn't it? So I didn't get any distinct.
The dark green
Yeah,
stayed on top.
dark green stayed.
Yeah.
Mine worked.
Yours worked? Oh, what did you do differently? Maybe she just believed. You know? You get the orange band as well?
Yeah.
Cool. All right. So sometimes it'll work, sometimes it won't. You know, that's just the nature of doing experiments over and over again, right? The great thing about, well, I guess the great thing about science is you can do it over again if you have to, right? It might be expensive in a workplace, you're not thinking that you have to do it, right? I always found really annoying. Someone messaging me. I always found really annoying was labs where the teacher basically says, you're screwed because these are your only results. And I'm like, well, you know, I should be able to do it over if I want to, but you know. All right, so yes. There's your classic setup. Okay, so yes, they should elute in distinct bands, right? So you should hopefully be distinct, right? And if you get really nice tight bands and they come off and you can graph kind of the absorbance out specific wavelength as they come off, you should have a nice resolution, right? So the higher your resolution, just, you know, instinctively, we know higher resolution means, you know, a better experiment, you know, better quantification, better qualitative, you know, analysis of what we're doing. So resolution is how well your peaks are separated from each other. So if they're all smooshed together, right, then you know that they will come off at the same time and you won't get resolution of which one's coming off at what time, right? So you'd rather them be as separated as possible with the balance of not taking 75 minutes for each experiment, right? So when we go into HPLC, right, we are taking all of these factors that are almost like out of the hands of physics by itself, and we're, you know, kind of putting some human control of it, and we're going to be casing our column in metal. All the tubing will be metal, and we're going to have a pump, and we're going to force it through, And that way we can tweak certain parameters to get resolution the way we want and get narrow peaks the way we want, right? So if we force it down the column for high performance or high pressure liquid, hello, people coming in. Photography. Also, you know what I should make sure I do? Are you recording me?
No, I'm just.
Recording in progress. I've also forgot to post a video for last week, so I apologize. I'll post that as soon as possible. The whole YouTube upload thing, just like, okay. Also, if you can't hear me, people online, please let me know, okay? Let's keep going. So, yes. When we are able to get nice sharp peaks, we will call, when we get nice narrow bands, we will call them peaks, right? So I'll refer to them as bands, as peaks, right? Interchangeably, right? But when they get so narrow, they end up being peaks. Now you can tweak the data a little bit. If you zoom in on the y-axis, you can make them kind of rounded, right? So you got to watch it sometimes, but they're narrow enough for our purposes. This is your usual chromatogram here. So if you can see that there is no lumps between the baseline, right? So you get up to the top and you come back down, baseline just being your solvent, right? Which we keep as our blank. You would call it baseline resolved. All right, so what you really don't want is to see stuff scooching down, right? Or little humps in between, right? You've usually optimized your technique a million times and your element and your mobile phase, right? To make sure that it's nice and sharp, right? So anytime you guys do an experiment, they will have had this figured out like, years before, right? So each experiment has its own tweaks that you have to do sometimes. And each one will be different in the end, right? But what we hopefully will try to do with HPLC is have it in a repetitive manner with the same experiment over and over and over again. So you can compare it to standards. And so you can, have regulatory bodies approve of what you're doing. I'm analyzing the cigarettes. It's got this much nicotine. I can repeat that experiment 10 times. It gives me the same result, right? Oh, more people are coming in. Everybody's in. Oh, look, we've got 1, 2, we've got 7 people in the chat, in the online class. Yes, so when we integrate the peak areas, you will find that your peak area is proportional to the concentration of your sample. So you will have to use a standard solution that you know the concentration of. So when you measure the area, you can then compare it to the area of your other peaks in your analyte, or whatever your sample is, which contains your analytes, and you'll be able to determine the concentration. So the performance parameter we're going to talk about is called column efficiency or plate count. Now, I wanted to look up the history of what plate count meant. It had something to do with, why do we call it plates? It has something to do with back when we used to do, I looked it up for you guys. I wanted to see, where is it? I think it had something to do with distillation when they had actual plates between pieces of the column. Where is it? I had the whole thing nicely set up for you guys. Oh, there it is. Yeah, so just analogy to distillation columns, they had physical plates or trays between this to facilitate the separation of components based on differences in volatility. So that's why they call it plates for some reason. Now, you guys will know it as just a factor of how good your column is for the most part and how narrow your bands are. That will be what the plate count means, right? So this will characterize the performance of a column for a particular experimental application, depending on whatever analyte you're working on, and your setup, your stationary mobile phase, and size of your column will all change your plate count for the most part. So this set of, or the plate count itself will be part of a set of parameters called the system suitability test, which again, regulatory bodies like the Ontario government, stuff like that, when you want to report results, they want to know the results of your system suitability tests that you will be doing, on the regular to make sure that your column is actually working. So as you keep track of these different parameters, you'll notice that your column is degrading over time, and then you can replace it if you need to, when you drop below a certain baseline, right? So plate count is one of the big ones. So we're describing our system by the reference to our peak width, right? So we can describe our peak width in a bunch of different ways, in a bunch of different formulas that we'll talk about, and maybe I'll put on the board. So as we go down, we can get them in our heads a little bit. Have you guys ever done statistics yet? You guys done stats yet? You guys talked about like, you know, the 95th percentile, the 50th percentile, stuff like that. Oh man, stats is the type of math I could never get my head around, ever. Always gets me, right? I was tutoring someone for grade 12 math and he had a stats section. I was just like, I know what I'm doing. But you'll know the concept of the Gaussian or the normal curve, like the bell curve, right? So the perfect peak looks like a bell curve, right? And you'll have your nice standard deviation, which is half of the width measured between the inflection points on the curve. So if you have perfect peaks, they will look like a Gaussian curve, but we know the world is not perfect and we will not always get Gaussian curves. But the first formula we're going to talk about measures and assumes that our sample is giving us a Gaussian curve. So the first formula is your plate count and your plate efficiency. Good morning. I'll put them all on the board one at a time here. Because there are 4 of them, all with different, very minor differences. They should all be around the same number. And I'm not sure which one of the formulas your machine will choose when you're running HPLC. It will probably choose the one that is just like the most, I don't know, what's the word I'm looking for? Consistent, I guess you could say. As long as all your peaks are measured the same way, everything should be relatively fine within a couple percent, right? Or whatever your concentration is. So TR, retention time, TR divided by standard deviation, sigma squared. So that's your statistical definition of plate count. Statistical definition of plate count, assuming our curve is perfect. So it's determined by the width of the peak around the center. We normalize it with its retention time to diminish the effect of peak broadening, which is proportional to the time. So again, larger n, narrower peaks. All right, because if you guys notice, whenever you have a fraction, the smaller number on the bottom of a fraction gives you a larger number. Right, so smaller standard deviation, higher plate count. That makes sense? Right, when you divide by a small number, you get a big number. So if you look at the fraction there, beautiful. Okay, so the larger your plate count, the better. Okay, so far with this, and again, I will post, these slides are already posted and the video will be posted as well once I remember to do it. Sorry. Okay, so then practicality comes in, right? Because we are not going to have a perfect Gaussian curve every time. So we also have the USB tangent formula for plate count. This refers to the United States pharmacopoeia. So I probably will be using this in pharmaceutical applications. So it will be the formula for USB tangent will be 16 times the retention time divided by the width of our base. Now, I believe it is full peak width measured on the baseline between the tangents drawn to the inflection points of the peak and extended to intersect the baseline. So what that means is, where's my, I don't want lots of space here. I want people to be able to see on the camera. If I go this way, okay. So we have our peak. Here's our baseline. So W will be, so the inflection point is when the curve changes direction. Have you guys done your 12 calculus, whatever like that? So your inflection point, you're curving this way. You start curving this way, the point where it changes to the other curve direction, that's your inflection point. So your W will be on the inflection point, extended to the baseline. That will be your W. Cool? Yeah, okay, great. So it will be 16 times your retention time divided by W base squared. So this is 16 retention time divided by W base. And that will be your USP tangent. Now, theoretically, that should be the same as your standard deviation if you have a perfect Gaussian curve, right? So it shouldn't be a problem. You should end up having the same number if you have a perfect Gaussian curve. Okay, we okay so far? Get a little mathy, that's okay. So here we have some nice curves. And I don't know why, now again, the previous professor put this slide in probably to show these specific ones. So wherever the inflection point would probably be somewhere around here. So you'd extend that to the base of the column, and then for down here, the inflection point probably around here, and you'd come down. Oh, you know, I'm not, sorry guys, I'm not displaying my screen here. Sorry, one sec. Forgetting certain things. Where is the share? There it is. This one, screen 2. Sorry, online friends. Okay, there we go. All right, let's keep going. All right, so we have another one. Our full width at half height formula for plate count. So again, it'll be a retention time, and then our WH/2 will be the full width at half height of a Gaussian being equal to, oh, sorry, excuse me, full width at half height. So we go up to the half of the height, and we get the full width at that point. So this is our so it would be 5.54 TR over WH/2. WH/2. That is our full width. Let's just FWHH, full width at half height. That's another formula. Now, this should hopefully be equal to 2.35 standard deviations. It also works with USPs, United States Pharmacopoeia. Now, again, depending on which one you use, right, it'll probably be whatever your workplace is chosen. They all should give you basically the same number if you have nice narrow peaks. If you have weird tailing peaks, you know, you'll get different numbers from each of these, depending on which one you choose to use. Let's say you have an analyte that, you know, gives you a tail every single time, but if you, you know, if you're able to cut it off, if you cut off certain piece of the peak in the integration, you know, get the right answer. You can adjust whichever one of these formulas you choose to figure out which one will give you the best answer without you having to do manual math every time, right? So let the machine automatically do it. So there we are. Now, again, if you have a perfect Gaussian curve, this should give you the same number as the first formula. Right? But your curves will tend to lean one way or the other or have a tail, at least a little bit, most of the time. Oh, look, more people want to come in. Oh, cool. It gives me a little notification for trying to get in. That's good. Okay, I always want to just make sure I pause and jump into the Zoom just to make sure that everybody can full screen that. Yeah. Nobody's like saying, "Sir, I can't hear you." Oh, good. You guys will let me know if you couldn't hear me, right? All right. Let's go back here. So another formula. So formula C, and then finally we get to formula. And then just the same picture again. I guess full width at half height would be halfway up the curve. Okay, and finally, 5 sigma formula for N. So we end up, same thing, 25 TR, but W5 means, all right, stay with me. Okay. It is the full peak width measured on a line parallel to the baseline, but it is situated at 4.4% of the peak height. So they raise it up a little bit, and then they measure the width. So you notice this number will mess with you if you have peak tailing, because, can I zoom in a little bit on this one? If your peak tails a little bit here, right, you'll end up having this number be bigger, right, which you don't want. So I think you will, yes. Yes, it hides the, now that doesn't make sense to me. If it's narrower, you should have a smaller number here. So it should be, yeah, okay, smaller number. Yeah, the bigger your number, the smaller this will be. Yeah, okay, so. So yes, this will take into your account your peak tailing, which is what you kind of want to make sure you take into account most of the time. So I'm not sure why they call it W5 instead of W4.4, but I guess they rounded up to 5. But yes, so let's go back to our picture there. Let's put that on. So this is our 5 sigma formula, 25. TR over W, see this was slash, divided by W5. So that is our 5 sigma. All right, so if you have perfect Gaussian curve, this again should be the same as the first formula in terms of your plate count. All right, so if your peak has really, really aggressive tailing, the number on the bottom will get bigger. You'll have a smaller number, you have a smaller plate count. So again, it encourages you to have narrow peaks. All right, so you wouldn't want to use this if you knew your peaks were going to tail. You'd want to bring it in a little bit. Right, there it is again. So same picture. All right, so there we go. So all the different numbers you might need are on this slide. So whichever one you're going to use, we didn't just barely talked about there's a W5, 4.4% of the full height. Your full width, your width and height over 2, and then your retention time being at the height of the peak. So your retention time will be at the highest point on the peak. That's when you'll measure your TR. Good stuff. Are you missing any of these numbers? One? I don't think so. So looks like. All right, team. So I think on the test, I would just give you guys these formulas and you guys would just have to recognize which one's which. All right, so I said, use this formula to find the plate count for this peak. And you'd be like, give me the 5 sigma, plate count of this peak. You guys would have the formula. I just wouldn't label it. I just have it there for you and you would pick it out of the bunch and know what formula it is. Does that seem fair? It's fair. That's always my problem when I was doing physics tests, is I just didn't know which formula was which, right? Off the top of my head. So if I just had the picture, or at least just had the formula itself, I was able to figure it, no problem, right? So I want you guys to have that same opportunity. Anyone else trying to get in? No. All right, so this is what you might see when you're running your HPLC system. So a lot of this information you will find is completely useless, right? But some of it you will start to recognize once you know what you're looking for, right? So they will tend to have, if you look here, 5 sigma, right? Your tangent plate count, I'm not sure, oh, sorry, width at half height. So width at half height, your width 5 sigma, your width at the tangent, and your tailing. So your tailing being this little piece here, right? So if you do plate count with all these different methods, right? Your tangent, you would have again, it's measured in plates per meter of column, I believe. So you see the different numbers as we go down. All right, so what you might probably pick is the one that gives you the plate count or the highest possible plate count for whatever you're using. So let's zoom in here. So efficiency of plates per. So there it is. You notice you have your highest plate count when you do the USP tangent method. Now you don't want false senses of security, right? You don't want to just be losing parts of the peak that you want to integrate, right? But at the same time, you want to find a nice balance where you're getting high efficiency. So you hope that you pick the right method for that. So it all depends on what you're picking. And I wanted to look up specifically why I would pick a specific plate count method. I wanted to see, it was so use the statistical one when you have well-resolved symmetric peaks. But again, it wasn't getting very good answers, honestly, about which one you would use at a specific time. Full width at half height for peaks that are not perfectly symmetrical. So there we go. Now, and then you guys would look for the area under your peak. I'm not sure if it's listed here on this one here. But yes, so when you guys are using the HPLC, you'll find it will sometimes automatically integrate your peaks, which is nice. They give you the area under the peaks, but sometimes your peak, let's see if it's like, if your peaks are blended together a little bit, you have one that's just a little bit coming off here, you might get this area integrated instead of this one, which can throw you off, right? So sometimes you want to automatically like cut to here, but then you're also getting a little bit of a boost, this like hidden piece here that you're going to lose in this peak. So you guys are going to have all sorts of fun manually integrating later on, when you work on it. And I'm looking forward to hearing your stories about it as we go. But this week, I think you guys are just doing the 3rd week of your spinach, right? Okay, so your plate count depends on the efficacy. Again, this gets very technical, but I'll go into each one here. Of the re-equilibration of analytes between the mobile and stationary phase. So the more equilibrations that take place, the larger your plate count is. So what equilibration means is how many times your solvent, or excuse me, how many times your analyte can bounce between your stationary and mobile phase as it travels down the column, right? You want a longer column, right? Because the longer you go, the longer your similar molecules have a chance to all kind of group together and go the same way, right? So I'm not explaining that very well. So yes, there it is, like down here at the bottom, the law of large numbers, right? So the analyte molecules of the same type require an equivalent history. So they kind of do the same thing through the column together, right? On an average, group amount. That's why you get a little bit of the peak at the end, not just like coming off in one line, right? But the similar molecules will end up grouping together over time and have a similar jump history through the stationary phase of the column. Your particle size will change it as well. Your temperature will increase your your plate count, right? The more temperature increases chemical interactions, right, at a higher pace. So you get more jumps between mobile and stationary phase for your analyte. And of course, your mobile phase composition and viscosity, right? Column length, again, will give you a longer column, more resolution, right, as well. All right. So this is just showing the plate count for flow rate. You also notice your plate count will increase as your flow rate increases as well. So the harder you push through the column, the more you force through the column, the more your plate count will increase, right? So you're kind of forcing the similar molecules together in the same way. They're all coming together at the same pace. If you go too slow, it gives the molecules a chance to take different routes through your stationary phase, right? So they will end up making your peaks broader. And so that's all this graph means, right? But if you force them through too hard, you'll break your column. So you have to know the parameters your column can take, right? They can take a certain amount of PSI, but then you'll start noticing you get leakage and stuff like that. So I know one time at Centennial College, system wasn't working. We looked inside the machine, it was dripping all over the place. We didn't know why. Turned out someone had added a 0 to the milliliters per minute. So instead of being like 10 milliliters per minute, someone had set it to 100 milliliters per minute. And that's why the column wasn't able to handle it, because you're trying to force so much through this tiny little metal rod, right? Trying to force 100 milliliters per minute, it just wasn't working, right? So it was spraying everywhere. And then we also have our, again, HETP, height equivalent to one theoretical plate. Basically, it relates your column length to your plate count. It's this graph, again, it kind of shows you how your height kind of decreases over time, or how it goes. This graph just like, it doesn't get the point across very well, right? But I guess all these factors here, A, B, C, and D, what they're trying to tell you is they're all different things that can mess with your plate count, right? So eddy diffusion, right? These are different molecules taking different paths. Random diffusion, right? So there's similar molecules, but they're still going off in random directions, right? Mass transfer within particles caused by mobile phase, and then mass transfer with stationary phase. All these different things can make your plate count go down if they get too high. And this is not going to come up again, I doubt, so don't worry about it. What I want you guys to worry about is different parameters that can mess with your plate count: column length, particle size, temperature, mobile phase composition, viscosity, and flow rate. Okay, worry about things like that. And to understand why these things work, you'll have these 4 different things that can be effective. So these 4 different things, right? So when you increase all of those things, you decrease all those factors that can make your plate count go down, is what I'm trying to say. Okay. So what is the practical use of knowing the plate count? So you can know the age of your column, keep an eye on it, right? So if it gets clogged, if the stationary phase comes out in some way, get separation between the particles of the stationary phase, right? If you end up getting narrow channels dug through the stationary phase, so things come through at weird points because there's no blockage there, right? Then you'll start seeing your plate count go down. Okay. Your different brands of columns will give you, and they have the same specification depending on what it is. If it's a size exclusion column, if it's an ion exchange, if it's just your silica gel, right? They all different brands are gonna have a different plate count for sure. So you have to watch out whichever one you're gonna pick. And to that note, when you guys are picking a column, you wanna pick a column that is mass produced. You don't wanna pick a single use column that someone has made custom for you for cheap. Sheridan, they made that mistake. The lab boss is very cheap with her money at Sheridan, right? So she bought a column for $200, this one specific experiment, right? But it was a custom made single use column, right? But it had all these flaws in it. The plate count was terrible, right? Because she bought it for cheap. When you buy a mass produced column, where they make it in huge batches, you get more uniformity between the silica gel, whatever gel you're making. So each column will tend to be, again, once they have a really stringent process of getting them mass produced because it's very expensive to make a large batch at once. So they're going to have really good quality control, and they're also going to be consistent between. So if you want to buy one from the same brand, you usually get the same kind of column, you know, over and over and over again. But a single use one will throw things off for you. So you're never going to be able to repurchase it and just have your experiment run like normal. You're going to have to change all your parameters again every single time. So it's better to spend $1,000 on the mass produced column than spend $200 on one that someone just kind of poured, right? And then of course, practical usage tells you if your system is up to snuff to get whatever experiment you want to get done without having to tweak things too much. So for a new column, you should have a plate count of at least 8,000 per meter. So 8,000 plates per meter. And performant, I think that might be a brand, performant HPLC column. And this is very broad because it doesn't tell you what type of column it is and what we're expecting from the column, right? So yes, you're going to be checking your suitability of your column of the performance during, prior and after your experiment. So your different parameters would include your void volume, right? So remember what your void volume is. It's the volume when a molecule that is not retained by the column comes off, right? Your plate count, peak resolution, so how far away they are from each other, right? Your tailing or asymmetry factor. So tailing being, you know, if one end of the column, there's, oh, some people in here. In it. So tailing, again, we mentioned a bunch of times. I'll make sure the view of that camera. Oh, anybody else keep seeing themselves on camera? So tailing being, you know, that's not a very good picture. Let's do that again. Oh. Nice narrow peak at the beginning, but then at the end it comes off. There's a tail. Okay. Tailing or asymmetry factor. Asymmetry can also indicate if you have it lean a little bit, so it comes up and then comes down like that. So asymmetry that way isn't good, right? It means it's not coming off evenly. Gonna watch out for that. And you also want to make sure you're getting your repeatability of your peak area response upon successive injections of the same solution. So I put the same one in over and over and over and over again. I should get the same area response. I should get the integration of the peak should be the same every single time I send it through. So every time you guys do a standard, it should run the same. These are your system suitability assessments. And if you guys want to know, I looked up the tailing factor formula for your own interest. Where are we? Tailing factor. Tailing factor, where are you? Tailing factor formula is FB. So the tailing factor formula, for your own personal information, put it over here. This. Oh, sorry, T. It's not a W, it's a T with the reason. Put it over here. Right in the middle. I don't know if we talked about it. T is the width of the peak, 0.05, so that's 5% above the baseline. divided by 2 times F being distance from the peak maximum to the leading edge of the peak. The leading edge being the forwards part. So 2 times small f. So that would be, the F would be from the, what was it? The peak maximum to the leading edge of the peak. So here, distance from here, so leading edge of the peak, over here. This would be your small f. So the further your peak is, the bigger your tailing factor will be. That makes sense? So I don't think it comes in to your guys. It doesn't come into your actual, it doesn't come in right now, but if you guys put that into your report, I'm sure Bryn will be very impressed. Or Amanda, excuse me, be very impressed. Okay, so where were we? So yes, these performance parameters, most regulated laboratories will have some form of these that you have to take care of, right? And they'll be really important for reporting really good results to whoever you report to, right? Most of the time that will be to a regulatory body, Ontario government, public health, whoever. And if you ever want to publish a paper, right, they'll want to see these numbers as well. You okay so far? Doing all right? All right. So here is a wonderful book you guys can find if you want. The Great Bible, HPLC parameters. So HPLC by itself could be an entire set of courses, right? So we're touching on it in this course, and this course seems very focused on chromatography, right? But it's good to know, where you can look things up if you want it. I'm sure there's a copy around here somewhere, maybe in the library, probably in one of the science offices, right? So this is how you assess the suitability of your chromatographic system. Most of the time, I would ignore book like this and just Google things, but So stuff like this that you might want to know would be things like K prime or capacity factor. So your amount of substance in stationary phase divided by the amount of substance in the mobile phase. And then you can also have the same, again, these are really blurry sometimes. This one is the time spent in the substance by stationary phase over time spent in substance in mobile phase, same thing. So it's a K prime prime or K prime. I don't know where the -1 comes in, but your number of theoretical plates in a chromatographic column. These are different formulas you guys should recognize now. Retention time, peak width, peak width of peak at half height. So I forgot to mention in the previous slide there, he said, if you have terms, W and T in the same equation, they must be expressed in the same units. So width of your peak would be in minutes, right? Because your retention time is in minutes. So your peak width will also be in minutes, right? So if I have a 30-second gap between the peaks, sort of the bottom of the peak or the tops of the peak, they have to be in minutes as well, or you have to do some kind of conversion. Have you guys done gas equation conversions? Like the ideal gas law? Yeah, so you know how annoying those conversions are? Yeah, so if you want to avoid that with this, you should keep your W and T in the same units. Anyways, so here's a nice picture. We already kind of saw this, but it's always good to explore a little deeper. Half height, right? All right, let's keep going. So your R would be resolution between 2 chromatographic peaks. And your RR, relative retention time, and your tailing. Oh, there's a tailing factor. There it is. So with the peak at 5% height and the peak maximum to the leading edge of the peak. So here's that's a better version of that formula. Better picture than the one I drew. Leading edge. Oh, this would be the leading edge. Okay. I would call that the tailing edge, because the leading edge is like going that way, but whatever. Okay, so I'll make sure if you guys have all of these formulas, if you need them, like calculate the resolution of the peaks, right? You guys would want to know what they are, right? Calculate the retention time, which should be very easy, right? Because it's just 2 peaks compared to each other, right? your RF value. You guys have done that have you guys done thin layer chromatography yet? TLC? We'll probably come into that later. So relative retention time, you usually have a solvent front, right? So whatever your solvent is at the beginning, right? You divide your peak over the furthest part the front has gone to get your relative retention time. Every peak will have a different number. The relative retention time should be different and comparable for every standard that you do. So if you have a retention time of 2 minutes or 0.2 for whatever sample, you should have your standard be also at 0.2. So that's how you compare mathematically your retention times without just looking at it, right, and comparing. Okay. And these are just some of the parameters, but I think these are the ones you guys are actually going to need to know. So the actual instrumentation is what we're going to get into now. You guys will have a nice bottle of solvent, which you guys will recognize in the next picture. You have a pump to give you your high pressure. You inject your sample in the middle of your path, I guess you could say. You go into your column, and then you have your detector, and you'll also have a waste container and whatever signal you're using. So if you're using UV vis, if you're using fluorescence, if you're using mass spec, that'll be your processing unit. And then your display will show you your chromatic path. So let's go into what an actual one looks like. That's what you guys will see in the lab. They look, so many different versions of them. They vary wildly. So things you will definitely recognize will be the bottle of solvent on the top there. And your waste container will generally be on the bottom, right? So down here or on the ground. If it's a really experiment you guys do a million times, they want lots of waste. And of course, all the tubing and your injection port will be over here. The injection port will be this guy here. I should do a different color. Let's do red. Red. There is your injection port. Have you guys done any injections like this before? No injections? That's okay. It's kind of a niche skill that you will learn. So, the injection tube, you guys will be using a really small syringe, probably 20 microliters, maybe, I think maximum 80 microliters. So this little tube here, see, I wish I could draw on the screen. I need to use my laptop more often. So let's zoom in a little bit. So while you're leaving your machine alone, right? You have your mobile phase coming in here, coming in and going into your column, right? So it has a little circuit there. Your sample inlet is up here. So there'll be a little port, you'll stick the syringe in and you'll inject, okay? What'll happen is when you inject, you'll fill up this port, which is usually 20 microliters, right? And then it'll have a little waste ejection. So if you put in too much, at least you'll fill the port and then this will go straight to the waste. So this will go down to the waste, right? You'll fill it up and then you're going to turn the port to the inject position. And so what that will do is connect this tube here to the inject sample. So it connects down here. So this guy will go here, right? And so what will happen is your element will connect to the beginning here, everything through into the column. So the way it works is you inject, hold it in place, turn to the inject, then you'll watch the screen. When you get the red line showing the signal has begun, you pull it out and let it go back. That's how you inject a sample. So you guys will have your own chance to do that, hopefully at some point, very soon. Does that make sense to you guys so far? All right, so little things, you guys will have to rinse that syringe 3 times with your eluent and then your sample before you put it in, so you don't have anything in that sample loop that isn't what you want. All right, let's keep going. There's a wonderful tower you guys might see. Each of those towers being a different analysis module, depending on what you're trying to do. They also could have multiple pieces of it that look like they're separate that are actually just one piece. So generally they'll add a different one if they want to analyze in a different way. And so this is what you might recognize as an Agilent system or an Empower system. You guys will likely be using Agilent. I've never seen it in Power before. So your software will give you the control of the instrument itself. So your modules, your pump, your injector, your detector, and will do your injections in your prescribed sequence. That's only if you have an auto sampler. It'll do your data acquisition, usually do the analysis as well, so the integration of the peaks. And most of the time when we're doing HPLC, we're doing, like if we're doing it based on polarity, it'll be reverse phase chromatography. You'll have a mobile phase, organic, right? Non-polar, acetonitrile or methanol, and then your aqueous part of it, which will be your polar component. Just like any other chromatography, we're going to be tweaking it based on the experiment we're doing. So for an example, on this Eclipse C18, we have a column 4.6 times 50 times 5 micrometer particle size column. So I believe 4.6 millimeters wide, very small, 150 millimeters long is the column. And then the mobile phase 60-40 acetonitrile and water. A flow rate of 2 milliliters per minute, and you have a detector of 254. So I'm detecting at 254. What wavelength am I in? I mean, what light range am I in? Off the top of your head. UV. So most of the time we're doing UV vis detection for HPLC. 99% of the time. So in terms of elution, right? If we keep the same mobile phase the whole time, we have an isocratic elution. And then we also have gradient, which you talked about as well. So we'd increase the organic content to get our more nonpolar analytes off the column as fast as possible, or whatever phase we're trying to get them off in. We usually use UV vis for detection, and we'll get full spectrum for all retention points. Most of the time, you will pick a wavelength, right, that you guys will know your sample's coming off in. We might measure refractive index, and then mass spec. Mass spec being it energizes it, throws it through a magnetic system. It pulls it towards the sensor at different rates based on the weight. Now it's your mass spec. So it'll tell you a weight number instead of a wavelength absorption. And then we also might recover from our waste. Instead of going down to a waste tube, we might recover little fractions of it at the end because we don't necessarily destroy the sample if we pull it through the system. I want to cover it as well. Also, depending on how expensive your analyte is, maybe you don't want to get rid of it. All right, I think that's it. Beautiful. Okay. Ooh, a lot heavy stuff, right? All right. So let's go through some of those questions that we usually have posted here. I don't know. I like to go through all of them, but that's okay. I find it helps way better to like understand things if you can answer some questions. So I'll have my answer sheet so I can pretend that I know all the answers. All right. So in turn, instead of peak, what might we call it? What's that? Line? A line? Line.
Band.
Oh, sorry. Yeah. That's yes, band. Okay, perfect. All right. Resolution. So how would I define resolution? We have the mathematical formula we did a few slides ago, but what's resolution just as a concept?
It'll be separate.
Yeah, separation between what? Between the peaks. Okay. Okay. All right. Why do I need baseline resolution of my peaks? Why would I want my peaks to be separated very nicely? If they're squished together, what does it mess with? I want my peaks, right, resolved to the baseline. So I can integrate the peaks individually, right, and compare them to the standard and have good, is it qualitative or quantitative analysis for this one? Am I getting a number or am I just getting what it is? A quantitative analysis, right? So qualitative will be fine if they're smushed together, but I can't measure the actual number unless I have them resolved nicely, right? Okay, so what does plate count relate to? Also known as column efficiency. It means efficiency of the column, sir. So plate count as a basic concept, right, relates to the width of the peak around its center. So the narrower it is, the more higher your plate count will be. So higher values correspond to better column performance. So that answers the next question as well. If peaks are narrower, the plate count is larger, right? So narrower peak, larger plate count. All right, so which parameters are used for the practical calculation of the plate count? What parameters do we talk about?
Retention time.
Retention time is a big one, right? All on the board, right? So what's this symbol here?
Standard deviation.
Standard deviation, right? So that's the width from the center of the peak to the inflection point of a perfect Gaussian curve will be your standard deviation, right? What's the W of the base?
With space.
With the base of the column to the inflection points, okay? W H over 2
Is the width at half.
with the peak at half height, perfect. And then W5,
4.4% of.
Yeah. yes, width of the peak measured at 4.4% above the baseline. No idea why they picked 4.4%. It's probably some statistical mathematical thing they discovered over time. All right. All right. True or false? The square of the retention time occurs in all the formulae for the calculation of the plate count.
True.
I forgot all the squares here. True or false? True. All right. Beautiful.
Question.
Yeah.
Does that mean if we measure the width at any random point, there will be a different numbers outside the bracket, right?
What's this?
Like if we change the width at a random point in the height,
Right.
and then if we change the numbers that comes before bracket, then we'll have the same formula again.
I think that's why the numbers change so much, right? Is that they all kind of boil down to this one if the curve gets Gaussian, I think, right? So like a normal perfect bell curve, they all kind of boil down to that. I think that's what they're trying to do with the different numbers. We measure at different points for the most part. Okay. And the USB tangent formula. So the peak width, so which, oh, it's already labeled. That's fine. Full distance measured baseline between tangents drawn to the inflection point of the peak and sent to the intersect of the baseline. Okay. So we talked about this already, right? Just based on those on the board. Okay. What are 3 practical applications of knowing the plate count in chromatography? What does the plate count tell you? 3 things, or at least 3 things that you can use the plate count for. The age of the column. Okay, so the performance of the column based on the age, right? What about different methods or conditions? The different methods or conditions, if I change my elements a little bit, right? If I change my column, if I change the temperature, if I change the flow rate, right? I can optimize my plate count based on all of these things. So what generally you'll do if you're developing an experiment is you'll run a bunch of different ones. You'll tweak little parameters, watch your plate count go up, and you can even run a little graph, like plate count versus flow rate, plate count versus temperature, plate count this versus that, and you can watch wherever the peaks occur, and you can tweak your experiment, those perfect things. All right, so it'll be your different methods or conditions, and then finally it'll be your compliance with system suitability tests. Talked about this already, but we can talk about it again. So number of parameters. So a column, what about the column can change my plate count? Here's my tube of metal. What things can I change about that to influence my plate count? The length, perfect. Stationary phase, what can I change about my stationary phase? Influence the plate count. Particle size. Size, type, of course, of stationary phase, right? What about the mobile phase? I changed about the mobile phase. Oopsie. Wow. Composition of the mobile phase and the flow rate, right? And of course, yes, your length and diameter of your column as well will change things. So, okay, so how does the plate count depend on particle size of the stationary phase? What do you guys think? So smaller particle sizes give you a higher plate count. Why? What do you think? Oh my gosh. Hold on to a marker today. I like to think of it in terms of literally just like rolling around things in the column. So if I have big particles, right? This guy's going to travel further, right? Than if the particles were small, right? Right? He has less room to go, right? So, and also if I go off in random directions, boing, right? I have less chance that I'm going to diffuse randomly throughout my solution. And if I have smaller particles, it's less likely to bounce off, the particles and flow in random directions. So smaller particle size, higher plate count. So smaller particles gives you a larger surface area for interaction. You can jump more effectively from particle to particle. It's easier to travel, yet narrower peaks. Okay. We did not talk about rheodyne. Whew. Okay. Oh yeah, so this is on the most recent slide here. So this column had an optimum value of flow rate that was 2 milliliters per minute. So rheodyne, do you even come with there? Oh, I see. Okay, so that's if you go back to the slides, the rheodyne is where is it? This is the rheodyne, the injection method or the injection apparatus. That's the rheodyne. So the rheodyne is a device used to facilitate the injection into the chromatographic flow path, allowing for precise and reproducible sample introduction. This is called the rheodyne. Now, oh, there it is, right there. I missed the word entirely. Manual rheodyne injector. Okay. Back to the questions. Let's finish those guys off. Talk about your lab. How many questions have we got? Operating parameter, set point of the pump. So for questions 16 of the pump. Okay, so for question 15, the principal operating parameter of a pump is the flow rate. That's the answer to that question. Question 16, what's the principal set point of the injector? What do you guys think? That would be the injection volume. So for question 17, the set points, there are three. The three set points being the flow rate, injection volume, and the mobile phase composition. And lastly, how would you achieve a faster elution of the analytes in reverse phase HPLC by adjusting the composition of the mobile phase? Remember, reverse phase is a stationary phase polar or non-polar. So if I want the samples to come off faster, what do I do? So you increase the polarity of your mobile phase. So you'd increase it by adding more organic solvents, so acetonitrile or methanol. That would make it off. Oh, sorry, no, not the non-polar, excuse me. You increase the non-polarity to bring off the non-polar analytes, excuse me. So yes, you add more organic solvent. Beautiful. Okay, good stuff. So let's talk about your guys' lab this week. Should be I wanted to make sure I covered it because Amanda asked me to make sure you guys have a little bit of background. Where? That one, oh, you know what? It's on the Chrome. Okay, so let's jump into that. So you guys have done your fractions in your fridge, for spectrophotometric analysis. Back here. So you guys are gonna be using the Angelit single beam diode array spectrophotometer. You guys can have your different solvents for diluting your collected fractions. So why would I need to dilute a fraction? What do you guys think? I have my sample, I took off the column. Why don't I just put it right on the machine? Like, why do I have to dilute it? What do you guys think?
At some point, alpha concentration, it will absorb all the lights and
Yes, so if it absorbs too much, I get nothing through. If it's too dark, I can't see anything. So you'll see on your column, if you were to run a sample, right? And if you were to run a sample and it saturated the detector, that's what it means. You'll see this, you'll see it go up and go flat and then come back down. And that's an indicator that you have saturated your column or saturated your detector. You have to dilute your sample a little bit because there's no way to know where this peak ends, at least for sure. You can like assume it based on like calculus and stuff. You could do like a derivative of the formula if you got the curve, but we're not going to do that. We usually just dilute a little bit, bring it down, and then you'll get the sample. So in instrumental, a lot of my students are noticing that the fluorescence spectrometer is maxing out at 99999. And they're like, oh, it's very consistent. I'm like, like you're maxing it out. Right? So you have to dilute your sample a little bit. Now we're gonna have a reference spectra and absorption peaks. So you guys, I don't know if they're not going to give you actual reference samples. It'd be nicer if they gave you reference samples you could run and you could see the absorption and stuff like that. But they're just going to give you the reference spectra and absorption peaks. Right, so you're going to run them all. Basically, going to run a scan of the system. It'll tell you where the peak is, and then you say, okay, it absorbs at 400 nanometers, which matches beta carotene. So I know that this one is beta carotene, right? And you also have your chemical formula, so you guys can determine which one came off first. Right, so you have all these clues of what chemical came off, right? The elution time, or which one came off first, the wavelength of absorption, and of course the color and all sorts of things like that. And then if you really wanted to, you could run it through like a mass spec and get other clues as well, right? So here's just your when you run your machine, right? So you're gonna have your wavelength range of scan. Try to exceed 2 absorbance units for the absorbance, and then this is just instructions for how to label the pieces. Like that. I don't think this will be giving you guys much trouble at all, really. Yeah. You have your reference numbers, and yeah. So then for you guys' report, have you guys talked about your report format? I always like to give people advance notice what the report format should look like. There's all your different things. Yes. Okay, so this is a really nice your discussion questions. I want to make sure. You have discussion questions? Big count. Report, here we go. Equations, graphical instructions. Okay. This is your mark scheme. Is this still lab 1? Seems like a lot of. Okay, I'm experiment 2 right now. Okay, let's not worry about that stuff. You let your lab instructor tell you about your formats. Okay, so next week, tentatively, we'll do another quiz based on the previous stuff we talked about. Still trying to figure out how to make sure it's fair between online and people in person, but I'm definitely going to do the midterm and make sure everyone has to be here in person for the midterm. All right, I think that's the most fair way, especially since it's worth a lot of marks. I want everybody to be here in person because I want it to be fair for my friends who come to class, right? That you guys aren't able to cheat the same way that people online are, especially if I have no way of seeing your smiling faces online and I have no way of using lockdown browser, which I can't really see a way to use. When you guys, during COVID times, you guys do tests online? They have lockdown browser? Like how they stop you guys from cheating in online tests during COVID? Did they just not? Hey guys, were you guys not here during COVID? Oh, right, I forget. It's been a little bit, hasn't it? Back in my day, everything was online. All right, cool. So you guys, that lab is tomorrow, right?
Which next week is from week 2 to this week, right?
Yeah, I'll do everything. Well, yeah, I guess everything between week 2 and now. Sure. and then
It's
common
the
sense.
same Format again.
that?
It's the same format again.
Yeah, online, same format.
Same
And I'll extend the time as well. So there's a 15 minutes again. Okay.
Multiple choices or?
Yeah, and multiple choice. Yeah, maybe there's some multi-select ones as well, I think in there as well. Maybe some matching. I don't think any matching ones are set up. All right. Are there any questions? Yeah,
You post the answer to the question sets?
I would love to. I will post them. Sure. No problem. Yes. All right, team. Have a lovely day. I'll see you guys next time. I'm gonna stop this night meeting and I will post the video once it has compiled. Goodbye, online friends.